Before we get into too deep into the weeds of figuring out where horizontal asymptotes are of functions, let's develop some very fundamental statements here. In fact, it's going to kind of build on what we just looked at with that function 1 over x. Well, we saw from the graph that we were able to say that the limit as x grows increasingly large, or as x approaches infinity, of the function 1 over x was equal to 0. And you can see that laid out here. As x is growing really large, as x grows infinitely large, f of x grows infinitely small and is in fact approaching 0. So as x gets really large, 1 over x gets really small, and in fact it's approaching 0. So let's take a look at some of these other functions we have. Let's consider the following functions as they approach our idea here of infinity. And I'm going to look at as we approach positive infinity and also as we approach negative infinity. Well, what if I take the limit as x approaches infinity of the function 1 over x squared? So again, as x is growing large, 1 over x squared, if this denominator piece right here is getting larger and larger and larger, then that means 1 over that number is getting smaller and smaller and smaller. And in fact, this also equals 0. In fact, it's going to 0 faster than this function right here, but it is also going to 0. Well, if I take a look at the limit as x approaches negative infinity of 1 over x squared, well, as I grow towards negative infinity, the squaring actually kind of negates any idea of the negative of this. And so I am still growing infinitely large here in the denominator, and so that is headed towards 0. All right, let's just kind of keep generically looking here at what happens if I have x to a power in the denominator, 1 over x to the fourth. Again, as I grow large, this denominator piece right here grows large, and that forces this function to 0. And if I take a look at the limit as x approaches negative infinity of 1 over x to the fourth, once again, and this could have been x cubed. I don't mean to imply that just only even exponents are going to do this. This could have been x cubed, and I'd have the same result, that as this denominator grows increasingly large, 1 over that is growing increasingly small towards 0. One more case to look at here. Let's take a look at the limit as x approaches infinity of 1 over the square root of x. And remember, I can write the square root of x as x to the 1/2 power. So I've got this same idea floating around here. It's just a rational exponent. It is an exponent less than 1. Well, as x grows infinitely large. Again, it's not as quick as these particular functions up here, but the square root of x does grow larger and larger. It does not have any kind of bound acting on it. And so 1 over the square root of x is headed towards 0. What about the limit as x approaches negative infinity of 1 over the square root of x? Well, if I'm looking at the square root of x, I do have an issue when I start talking about negative numbers, because x is going to have to be greater than or equal than 0 to take the square root of it. And in fact, because it's in the denominator, I've got to throw out 0 as well. So for this particular function, its domain is only x larger than 0, which means there is no approaching negative infinity. And so this particular limit right here does not exist. But for every other case, as I approach positive infinity and negative infinity, I can really state all of this here as just kind of some general rule. And so let's take a look and say if n is greater than 0, so if this positive value of n, we'll talk about negative exponents later, and obviously negative exponents are going to behave differently. If I had x to the minus 3, that would go back to the numerator as x to the positive 3, and in fact it grows without bound, and so there is no asymptote there. So for any positive value of n, which is going to be a rational number so things like the 1/2 power, this will still apply, then automatically the limit as x approaches infinity of 1 over x to the n power. So no matter what power I was raising x to, 2, 4, 1/2, the function was growing towards 0. And then the same thing is also true for n greater than 0, which is going to be a rational number. I'm setting up a statement here to say the limit as x approaches negative infinity. As we saw here with 1 over the square root of x, I do need to state such that x to the n is defined for all x. So things like x squared, x to the 4th, that is defined for all x. Then the following statement is true, that the limit as x approaches negative infinity of 1 over x to the n is also equal to 0. So if I'm going out towards negative infinity, as long as I'm within my domain, I'm also approaching 0 right there. And this idea over here in this kind of bottom right area, that the limit as x approaches infinity of 1 over x to the n is 0, and for negative infinity, as long as it goes out there, that this function is also equal to 0. It gives us a really important statement that we'll look at in the next video to go find the horizontal asymptotes of more complex rational functions.